All right, pre-calc. Welcome to the last lesson, which is part 2 of 14.4, tangents and derivatives. Buckle up because this gets a little bit heavy with the algebra, but it is very cool stuff. Hopefully you find value in it. So we have 2 examples to do, but notice example 6 has kind of a few parts to it. So let's get into it here. So we have 2 examples left. Notice though that nothing is changing as far as what we are studying. We continue to study the limit as a difference quotient. We define it a little bit differently with these guys, but it looks the exact same. So for the last part, we're applying what we know about derivatives and instantaneous slopes of a curve to be able to apply it to anything. So instantaneous rates of change. So example 5, we have a geometry problem. Example 6, we have a physics problem that involves instantaneous velocity. So here we go. Example 5 deals with instantaneous rate of change of f with respect to x at c. So it's just saying that we're going to make a benchmark someplace and we're going to look at the instantaneous rate of change from someplace on the function to that benchmark. So if you read through example 5 there, it says the volume of a right circular cone with height h equals 9 feet and radius r feet is what is that supposed to say? Oh, is this sorry, that's a little bit confusing. So the volume is equal to essentially 3 pi r squared. If r is changing, find the instantaneous rate of change of the volume with respect to the radius at r equals 2. So it's basically saying that we have this cone here that has a radius of 2. But from that benchmark, it's going to be changing. So it's either going to be growing or getting smaller from that place. And so what we want to know is how fast is the cone's volume changing with respect to the radius of its base. Okay, so they were nice enough to give us the volume formula here. So we have which is 1/3 pi r squared times h. But in this case, since we know our h is 9, we could plug that in. And so they plugged it in. And so when you plug that 9 in, 9 times a third is 3. So that's how they're getting 3 pi r squared for their formula for their volume. Okay, so we're going to use that. Okay, so to figure this out, we basically just need to find the instantaneous rate of change. How fast is this thing changing with respect to what we already know? So to do that, we're just going to plug it in. Okay, so we're going to use our f of x formula, which is essentially, in this case, I guess it would be v of r, I guess is what it would be in this case. The volume as it relates to r. And then we're going to take that whole thing evaluated at 2, so v of 2. Okay, because we want to compare it to 2. So that's our change in y, and then our change in x will just be x minus 2, but in this case, x is r, so we'll just call it our r minus 2. Okay, so now we're just going to plug in. Okay, so let's plug in what we know. We know v of r. v of r is 3 pi r squared. It's just the function. And then if we evaluate that with a 2, plug a 2 in for r, we get 2 squared, which is 4 times 3, which is 12. So it's 12 pi, so we're going to subtract 12 pi. Again, what I did to find that was I just plugged a 2 into this guy. Okay, and that's v of 2. And then we're going to divide that by r minus 2. All right, so let's just simplify this out just a little bit. Know that pi is just a number. But we can take that number and a 3, looks like, out of both of these terms. So if I do that and take this 3 pi out, what I'm left with is r squared minus 4, which is nice, and then r minus 2. So this thing would factor to 3 pi r plus 2, r minus 2, all over r minus 2. These cancel, and I'm just left with 3 pi times r plus 2, but again, we're comparing this to r at 2, so I'm going to plug a 2 in. So if I plug that 2 in here, I'm going to get 3 pi times 2 plus 2, which is 4, so that I end up with 12 pi as my answer. So what does this answer mean? This answer means that as radius changes, as my radius goes up by a foot, the volume of the cone goes up by 12 pi. If it shrinks by a foot, it goes down by 12 pi. Okay, so the rate of change in regards to 2 is it's for every foot from 2 is going up at a rate of 12 pi. Okay, so that's a geometry example. Let's cruise on to this guy. This is the beast. Instantaneous velocity. So hopefully you guys know a little bit about velocity. Velocity is basically a vector quantity. It is speed, right? It's a speed calculation and technically a direction. So speed and direction. So just a review of what velocity is. And so to calculate out what a speed is, we need to know distance and time, right? So it's the change, essentially what we have is the change in distance over the change in time for velocity. So what's interesting about instantaneous velocity is we know that as things, float through space, as like if you were to drop something off of a building or something like that, that thing is going to continue to accelerate towards the ground. Accelerate meaning it's going to gain speed, right, as it goes toward the ground. But there will be a little bit of wind resistance, obviously, actually quite a lot of wind resistance eventually, but that'll throw this off. So this calculation, I guess, maybe takes into consideration a little bit of wind, but I doubt it. I think we're looking at, like, if we were in a vacuum, this is how this thing would travel. But anyway, that's kind of all beside the point, but an important background that velocity is the change in distance over the change in time. Okay, so in physics it is shown that the height s of a ball, so they called height s, which is interesting, so that's like the distance from the ground, is thrown straight up with an initial velocity of 80 feet per second. And let's see if I can see what happens if sorry guys, thought I had a picture of this for you guys, but I guess not. Maybe there's a picture on your notes, but anyway, 80 feet per second from a rooftop that is 96 feet high. The volume, the formula for this is S of t, so the height in regards to t, time, is equal to negative 16 times t squared plus 80t plus 96, where t is the elapsed time that the ball is in the air, and the ball misses the rooftop on its way down and eventually strikes the ground. So if you don't have a picture of that, we're on top of this 96-foot building. We throw something up, and then it comes down and hits the ground, right? So that's the kind of the scenario that we're running. So first off, what they ask us to do, it says, when does the ball strike the ground? That is, how long is the ball in the air? So to figure this out, I mean, this is essentially a parabola, right? So if you were to graph this thing, we could do it the long way. You can go on Desmos, you can graph it there. But remember that if you graph one of these quadratics, a place where it's going to hit the ground is going to be a 0, right? So if we relate everything to 0, that's going to be a place where we have a 0. So what I need to do to figure this out is I need to factor this. Okay, so for part A, I'm just factoring. I'm not getting into any of what we've learned about instantaneous stuff yet. I'm just going to factor it. So if I factor it, okay, we're going to set this to equal. It says when does it strike the ground? So I want it to equal 0. Okay, so if I factor this out, it appears that 16 goes into all of these. So I can take a negative 16 out. So if I take a negative 16 out, what I'm left with is t squared plus 5t. Oh, sorry, I took a negative out, didn't I? My mistake. Minus 5t minus 6 is equal to 0, right? So then I can factor this nicely. So I have two things that multiply to give me negative 6, add to give me negative 5, which would be negative 6 and positive 1, right? So this would factor to negative 16 times t minus 6, t plus 1. The things that make this go to 0 are 6 and negative 1. I can't have negative 1 seconds, so I'm going to disregard that answer. So I'm going to say it takes 6 seconds for it to hit the ground. Okay, so that's part A. Part B, at what time t will the ball pass the rooftop on the way down? So basically, where does this happen? Okay, so we can adjust our 0 here to just be essentially where we started, which is 96 feet. Okay, so instead of 0, I'm going to do the exact same thing I just did, but instead of saying equal to 0, I'm going to say equal to 96 feet. Okay, so then we'll do the same thing. What's nice about this, though, is we have already done most of the work, right? So, actually, scratch that. I mean, it's even easier than that. Since I have 96 here, if I want to get rid of these 96s, I can subtract 96 from both sides, right? So if I do that, that's gone, and I'm just left with this guy. Okay, and I know the negative 16 goes into both, so if I take that out, I'm left with, and a t out, I'm left with t plus 5. And I should not say plus. I don't know why I keep wanting to do that. This would be t minus 5, right? Okay, so what makes either one of these factors go to 0 is going to be a solution. So either 0, which would make sense because that's where we launch from, right? 0 seconds. Or 5 are the two answers to that guy. But it says they want to know what time it passes on the way down. So we'll disregard 0. Can't be 0. Has to be 5 seconds. Okay, so now we know something about the times. Let's keep cruising here. Let's go to velocity. What is the average velocity of the ball from t equals 0 to t equals 2? Okay, what they want to know here is at 0, we can set this whole thing to the original. So if I plug a 0 in for t and plug a 2 in for t, I can figure out what happens at those two time frames. So I'm just going to do that. If I take negative 16t squared plus 80t plus 96, okay, and then I evaluate that at 2. So I don't know why I just did this, but let's just start this over. Sorry, guys. Let's just evaluate it at 2. So negative 16 times 2 squared, right, plus 80 times 2 plus 96. I can take that and I can subtract this evaluated at 0. Well, evaluating at 0 is easy. The first two terms go to nothing and it's just 96. Okay, so it's the average velocity. Velocity is the change in, so again, change in distance over change in time. This gives us the change in distance. The time frame here was 2 minus 0, right? So 2 minus 0, which is just 2. Okay, so if we evaluate this out, we end up with 192 minus 96 over 2, which is equal to 48 feet per second. Okay, so the average velocity, so over a time frame, which is typically what we calculate in basic physics and stuff like that, a lot of times that's all we really care about is the average velocity. But over a 2-second time frame, the average velocity that is experienced from 0 to 2 seconds is 48 feet per second. Okay, but what if we want to know what the instantaneous velocity is of the ball at any particular time, any particular point on its journey? So think about this. The speed of the ball, when you throw it off this building, is changing as you go, right? You go up here, it gets to some flat place, and then it goes down and accelerates faster and faster and faster toward the ground, right? So what is the instantaneous velocity at any point in time? And it's important to remember that when you're graphing this, this is a distance versus time graph. All right, so just to have that visual. Okay, so what they're asking me to do here is to find, whenever you see this instantaneous thing, you're finding a derivative. Okay, you're finding the derivative. So let's find the derivative. Unfortunately, they don't tell us a time frame that they want to know this instantaneous velocity for. So it's not like saying, what's the instantaneous velocity at 2 seconds or something like that. It's saying, what is it anywhere? So you have to come up with an equation that works for anywhere on the graph. Okay, so that's what a derivative helps us to do. So to figure this out, I'm going to find, since they label this st here, what I'll do is I'll find st, s of t, and I'll subtract s of t1. We'll just call it, that's what they did like in the textbook example, so I'll stick with it even though I don't like it. So it's just saying sometime 1 that we use to plug in. I would use probably, I don't know what I would use there, but that's just confusing to have 2 t's in here. Anyway, that's what they did. I'm going to keep it that way in case you're looking on with a book or something. Okay, so this is all going to, so this is the change in y, right? Change in y, and we have to put that over the change in x to figure out the instantaneous velocity. It's the slope. So the change in x here is just what we're evaluating at, t minus t1. Okay, and unfortunately, again, we don't know those. But we do know what s of t is, right? So here's where this gets very convoluted quickly. I'm going to plug in s of t. So negative 16t squared plus 80t plus 96, right? And then I'm going to subtract s of t1. So I'm going to plug a t1 in for t. Okay, so I'm going to subtract negative 16t1, which I have to count different. I have to consider that different than t, right? t1 squared plus 80t1 plus 96. Okay, all over t minus t1. Okay, so now I just need to simplify things here a little bit. Okay, so I'm just going to change my signs real quick. So I'm going to zoom in here a little bit, see how this goes. So this is the same thing as negative 16t squared plus 80t plus 96 plus 16 t1 squared minus 80 t1 minus 96. So in doing that, okay, I just distributed that negative sign out. I can get rid of this 96. Everything else I have to keep in there because it is essentially different terms. Okay, so I'm just going to rewrite that real quick. So I have negative 16t squared plus 80t plus 16t1 squared minus 80t1. There's a 1 there, even though you can't see it. Okay, so now what I want to do, and again, this is all over, don't forget that this is all over. See if I can change colors here, make sure that works. This is all over t minus t1. Okay, so I want to try to simplify this. It appears that 16 goes into all of those, right? In fact, a negative 16 could come out of all of them. And so if I do a negative 16 and take that out, I take a negative 16 out, I'm left with t squared minus 5t. All right. And then here, if I take a negative out, I'm left with negative t1 squared and then plus 5t1. So I just took a negative 16 out. I'm going to ignore this bottom, but I will bring this back in here shortly just to kind of keep this a little cleaner. Okay, so let's see if I can combine a couple of things here to find a difference of squares or something like that. Like what can I do to simplify this a little bit? So if I rearrange this a little bit, I can actually write this as t squared minus t1 squared, right? And then I can keep that negative 5t plus 5t1, right? So I just rearranged it a little bit. Don't forget the negative 16 still out here. So here I have a difference of squares. Okay, so this is the same thing as t. Sorry, here, let me get this. Make this have a little bit more room here. So this is going to be the same thing as t minus t1 and t plus t1, right? Difference of 2 squares. And then here I can take out a negative 5. And I'm left with t minus t1. All right, so I simplified each of those. Don't forget the negative 16 still out here. Okay, and then what I can do now is this whole thing is over t minus t1. Now, bear with me, guys. I know this is a little bit messy. I can now cancel any t minus t1s, right? So I can take it out of this guy. As long as it's in this term, I can take it out of here and take it out of here. So what that leaves me with after all of that is negative 16, right, on the outside of this, and then I have on the inside here t, and be careful here, this is a separate term, right, so I have to treat that 5 as something that's inside parentheses here, so this would be t plus t1 minus 5. That negative 16 is applied to everything, so if that helps make sense of that. Okay, so now what I have just found, and I'm not quite done because I still have to plug in a t1, right? So I have to plug in a t1 for t because that's what I'm trying to find. So all of this was based on instantaneous velocity at t1, right? So I'm going to plug a t1 in for t, and if I do that down here, if I plug a t1 in for this t, I get this. Negative 16 times 2t1 minus 5. Alright, so that is my equation for my instantaneous velocity of the ball at time t. Notice I did not give you nearly enough space to do that calculation. Whew! Okay, so that is part D. Now, what they want us to do after that is use that for the next few questions. So it says, what is the instantaneous velocity of the ball at 2? Well, now I can just plug a 2 in for t1, right? So I'll do that. I have negative 16 times 2. So I'm just plugging this 2 into this formula for t1. Okay, so when I do that, I get negative 16 times 4 minus 5, which would just be negative 1, which is equal to 16 feet per second. So this is really cool to have this kind of math available to you, because now you can look at a distance versus time graph that has a curve on it, and you can tell exactly what the instantaneous speed is at any point in the graph. So at 2 seconds, the thing's traveling at 16 feet per second. So let's look at F here. It says, what is the instantaneous velocity of the ball equal? Oh, when is it equal to 0? Okay, so it's essentially asking, when is this instantaneous? 0. So I can set it to equal 0, right? So negative 16 times 2 times t1 minus 5 equals 0. Okay, so I'm just going to solve this. So I'm going to move that, divide both sides by, essentially just divide both sides by negative 16 for F. And if I do that, then I get, actually, do I want to do that? Let's just distribute this. If I distribute this out, what do I get here? I get negative 32 t1 plus 80 is equal to 0. So yeah, let's just move that 80 over. I guess we could have done it earlier. It doesn't matter. Negative 32 t1, okay, that's just some time frame 1, is equal to negative 80. So t1 is equal to negative 80 over negative 32. And when I do that out, it actually comes out pretty nice. It's 2.5 seconds. So at 2.5 seconds, the velocity is 0. Okay, so can you imagine where that is on the picture? Hopefully you're saying, yeah, right here at the top, right? The velocity goes to 0 because it's turning around, changing direction. So it happens at 2.5. Okay, so then G says, what is the instantaneous velocity of the ball as it passes the rooftop on the way down? Okay, so this here happens, we need to figure out when this happens, right? When did it cross here? But luckily, earlier in this problem, we did that. It says, at what time will the ball pass the rooftop on the way down? We said 5 seconds, so we're just going to evaluate this at 5. Negative 16 times 2, 5 minus 5. So let's figure out what this is here. So when I do this, I get 10 minus 5 which so I'm getting this is equal to negative 16 times 5, which is equal to negative 80 feet per second. The negative sign here is just talking about a direction. We are now going down toward the Earth at 80 feet per second. Okay, so there's the instantaneous velocity. And again, negative sign just means change in direction from upwards to downward. So now we're headed toward the Earth. And then H, what is the instantaneous velocity of the ball when it strikes the ground? All right, so when it strikes the ground, I believe we figured out what time frame that was earlier on, and that was 6 seconds. That was our first question there. So I'm just going to evaluate this at 6. Negative 16 times 2 times 6 minus 5. This is 12 minus 5, which is 7, so negative 16 times 7, which is equal to negative 112, I believe, feet per second. So on your homework, I'm not sure if they're going to want you to put that negative in or just say 112 feet per second in the negative direction or toward the Earth. Whew. So you guys, the hardest part of doing one like example 6 is figuring out the derivative on part D. Once you know the derivative, it's just a matter of plugging the pieces in. But once you have that, it's very handy because then you can use it to determine what happens at any point in time, which is what they're trying to get you to see, how valuable the derivative is. Anytime you want to know what happened on that journey, as long as it's a fair representation of the journey, you can use the derivative to figure out what the speed was at any point in time. So super handy stuff. This is one of the big takeaways from the beginning of Calc 1. Okay, so that's it, guys. This wraps up pre-calculus. I hope you guys go on to Calculus 1. I think it's a very fun subject. So yeah, spend some time. If you're going to do that, spend some time with the derivative rules, as I've pointed out. And it's been a great year. I'll check in with you guys next time.